Today you're going to be learning about an area of astronomy called spectroscopy. Spectroscopy is really a tool. It's a way that certain astronomers study the sky. Before I explain what spectroscopy is and how it works, we need to review a few concepts. So the first concept we're going to review is the electromagnetic spectrum. So this diagram should look familiar. What it's reminding you or showing you is that light comes in many different forms. So you can see here that there are different types of waves. There are radio waves, microwaves, infrared, visible, UV, X-ray, and gamma ray. And it's actually all the same type of ray. They're all an electromagnetic wave that travels through space. And the only thing that makes radio waves different from microwaves, different from X-rays, is their size. Radio waves have much longer wavelengths, which means they also have a lower frequency, whereas gamma rays have a much shorter wavelength, but a much higher frequency. Visible light, you might remember, is only a tiny little portion of the electromagnetic spectrum. Last but not least, what makes blue different from green, different from red? Again, it's wavelength, right? So colors they're all just different types of light rays. What makes them different is the width of the wave. Our eyes interpret longer wavelengths of light as being red, and they interpret shorter wavelengths of light as being blue. Now, the second concept I want to review with you is the concept of refraction. And we studied refraction when we started Unit 2 on seeing into the sky, and we looked at lenses. Now, hopefully you remember refraction is simply when a light wave hits some boundary between two different surfaces or two different mediums, and it changes direction. Right? So we saw that most frequently with lenses. Right? We looked at converging lenses and diverging lenses. So we know that when light hits some kind of new material, whether it's going from air to glass, or glass to air, or glass to water, or water to glass, so on and so forth, it bends. And that's called refraction. So I'm going to take the concept of electromagnetic spectrum and refraction and put them together and tell you about prisms. And you've probably seen prisms before. Sometimes raindrops can act as prisms in the sky. Sometimes prisms are in chandeliers. But a prism is a special piece of glass or some other material that's going to break up light. So what do I mean by that? Let's say I have a beam of light hitting this glass prism. And in that beam of light is a mix of all the different colors. And our eyes, when light hits our eyes and that light has all of the different wavelengths, our eyes actually see that as white light. So when we see bright white light from the sun, for example, although it is slightly yellow, what we're really seeing is a mix of all the different colors of light. Now, here's the thing. You'll remember that different colors have different wavelengths. And what that means is that they actually refract differently. And so this beam of light hits the prism, and you can see violet refracts the most, it bends the most, whereas red only bends a little bit. And so what that means is that the different wavelengths of light actually get separated from each other. And so we can see all of the different wavelengths. That's why sometimes in the sky you see a rainbow. If it's sunny out and moist, or it's just rained, a raindrop can actually split the sun's rays into a rainbow. Pretty neat. Okay, so what does this have to do with astronomy? Well, it has a lot to do with astronomy, because what astronomers do is that they study objects in space by looking at the light from those objects through a prism. So, for example, in the diagram down here, what I'm showing you is, this is a star, right? And some hypothetical astronomer dude is looking at that star's light, but instead of just looking at it, he's going to pass that light through a prism, right? And break it up into all the different wavelengths. What would you expect to see? Well, you might expect to see a rainbow, right? That light from the star It's very bright, it looks white, it looks like there are going to be all the colors there. But that's not what you get. You get an almost rainbow. So it looks like a continuous rainbow of color coming out of that star, but then there are these black spots, and those black spots are called absorption lines, as you see right here. And those absorption lines tell us a huge amount of information about the star, and that's why scientists do that. So before I explain to you what we can learn from the absorption line, you need to know a little bit about stars, and I need to reteach you some chemistry. So we're going to do a very, very short lesson on stars. Stars are basically big burning balls of gas. In the middle is where you have really the fire inside the star. And that's just a whole bunch of nuclear explosions going on over and over and over again. And then surrounding that fire are clouds of gas. Right? So there's just these clouds of gas, not glass, surrounding the fire. So in this gas are different atoms. Now hopefully you remember from chemistry that atoms are the building blocks of matter. They're tiny little particles. In the middle of an atom, you have the nucleus, which is filled with protons and neutrons. And then around the nucleus, you've got energy levels, which are rings. And on those rings live electrons. So I'll make this atom have, say, just 2 electrons. It's going to be a small atom. So what happens? Well, the fire is producing a whole lot of energy, right? Nuclear explosions galore inside the star. So that energy is leaving. I'm going to pretend that over here is the big fire inside my star. Okay? So energy is leaving that fire. Right? It's leaving that fire in all directions. Now, you've seen this in different examples before, especially with the photoelectric effect and film photography. These electrons can absorb energy. And what happens when they absorb energy is that they jump up an energy level. But here's the big thing. They can't just absorb any amount of energy. They can only absorb energy if it's exactly the right amount to bring them up to the next energy level. And what that means is that each electron in each atom has a certain amount of energy that it's capable of absorbing. And that corresponds to a specific wavelength of light. So it could be that this particular electron in this particular element can only absorb energy if it's hit by a wavelength at 535 nanometers. Now, what does wavelength determine on the electromagnetic spectrum? Color. So it could be, for example, that this electron can only absorb wavelengths of a very, very, very particular dark blue. So, can you predict yet what absorption lines mean? Make a guess. Absorption lines are these missing black sections on a star's absorption spectrum. That's what this is called, is an absorption spectrum, that show where specific wavelengths were absorbed. So for example, right here, there's a pretty strong absorption line. That means whatever this wavelength is, that particular wavelength of light was absorbed by one of the chemical elements in the star. Now, here's the cool thing. Each element can only absorb a specific pattern of wavelengths. So, for example, you'll see over here that calcium absorbs 2 very specific wavelengths in the blue-purple region. So what does that mean? Well, that means that this star has to have calcium in it. So even though this star might be hundreds of light years away, which is incredibly far away, we can actually tell down here on planet Earth what elements are in that star based on its absorption lines, right? Depending on what colors are missing when we pass that starlight through a prism, that tells us which chemical elements are in that star's cloud and absorbing specific wavelengths of light. So here you just have more examples of what absorption spectra can look like. Now you should be able to look at these, for example, and tell that these two stars probably have very similar chemical composition because they have very similar absorption lines. That means there are the same elements in their clouds. Now, this star, you'll notice, has all the same absorption lines as the one below it, but it also has others. That means it has additional chemicals in that cloud of gas. So the last concept today is just to show you that there are two different ways of representing an absorption spectra, or an absorption spectrum. Spectrum is the singular, spectra is plural. So we can show it as a band of color, which shows us all the colors in the rainbow, and then a black band where specific colors got absorbed by the gases. Or we can graph the actual energy coming out of that star for specific wavelengths. And where you've got these dips, you can see those correspond to the black, well, these aren't overlaid very well, but they would sort of correspond to or represent the same thing that the black lines do, which is specific wavelengths where there was less energy coming out of the star.